Hey everyone, get ready, because today we're diving deep into a world where robots are practically developing a sixth
It's
sense.
the sixth sense.
Yeah, like the ability to predict and prevent their own slip-ups. We're taking a close look at this really cool research paper. It's called Code as Monitor.
Code is monitor.
I know, right? The title sounds kind of like robots are taking over the coding world.
Taking over the world.
Uh-huh, not quite.
Mhm.
But don't worry, we'll break it all down. It's definitely a fascinating approach.
It is, yeah.
Okay, so picture this. We've got a robot chef, right? And its task is to carry a pan with a live lobster over to the stove.
Oh, a lobster.
Yep, a live one. Now imagine two different scenarios. First, the lobster, feels the heat and decides to make a run for it. Jumps right out of the pan.
Makes a break for freedom.
Exactly. That's what the researchers call reactive failure detection. The robot realizes, like, oh no, the lobster's gone.
Right.
But only after it's already happened.
Right, a little too late.
Yeah, damage control mode. But now, imagine the robot's got this code as monitor system.
Okay, code is monitor system.
This time, as it's carrying the pan, it notices even the slightest tilt.
It can sense a tilt.
Yeah. And because the system's been trained to understand what a tilted pan could mean, it knows there's a chance that lobster might try to escape. So it proactively adjusts its grip to keep that lobster safe and sound.
Pretty clever.
I know, right?
It really shows how this tech can not only react to errors, but actually prevent them. That's what's so groundbreaking about this research.
It really does. It highlights the difference between just like reacting to a problem and actually being able to stop it before it even starts.
Exactly.
And this becomes even more important in what researchers call open set scenarios.
Open set.
Yeah, basically think of it as uncharted territory for a robot. They encounter situations they've never seen before, objects behaving in unpredictable ways, that sort of thing.
Interesting.
They can't rely on just like pre-programmed responses. They need to adapt, think on their feet.
It's like throwing them into the wild and saying, figure it out.
Exactly. And that's where traditional robotic systems often struggle a bit. They can be slow. Their responses might be inaccurate because they're trying to like apply the wrong solution to a new problem.
Makes sense.
Which brings us back to Code as Monitor, or CAM for short.
Yeah.
This system is all about equipping robots with the smarts to handle these unpredictable situations. But how does it work? The name makes it sound like we're teaching robots to write code,
Haha. Teaching robots to code.
which already, I don't know, blows my mind a little.
It is a clever way to think about it. It's not exactly that robots are becoming programmers themselves, but at the core of the CAM system is what's called a vision language model, or VLM.
A vision language model.
Right. Essentially, the robot uses its eyes, so cameras basically, and this VLM, to process both what it's seeing and any instructions it's been given.
So like it's seeing and understanding at the same time.
Exactly. And then, based on that understanding, it creates a kind of internal monitoring system for itself. The researchers divide the CAM system into three modules: the constraint generator, the constraint painter, and the constraint monitor.
Okay, so three modules. Let's break those down one by one. What's going on in the constraint generator?
The constraint generator, think of that as the mission control. It looks at the task, figures out the robot's goals, and then sets up what we call constraints, or rules, that the robot needs to follow to succeed.
The rules of the game.
Exactly. So going back to our lobster carrying chef, the constraint generator might say, all right, your goal is to get this lobster to the stove without incident. Here are your constraints. Keep the pan level and make sure you have a firm grip.
Got it. So that's the ground rules. What happens next? The constraint painter. That name sounds a little artistic for a robot.
It is kind of. The constraint painter takes those rules, those constraints, and translates them into something the robot can easily understand.
Oh, okay.
But instead of words, it uses simple visual cues, points, lines, surfaces, that sort of thing.
Visual cues.
Yeah, so it's like creating a visual map or a set of instructions specifically for the robot, but using these simple elements.
A visual language.
Exactly. Each visual cue represents an important part of the task. For example, a point might represent the center of the lobster, making sure the robot stays focused on its precious cargo. Or a line could represent the angle the pan needs to be held at.
Makes sense. So this is where the code part comes in, right? With the constraint monitor.
You got it. This is where things get really interesting. The constraint monitor takes those visual cues and then, get this, it uses the VLM to actually write a program.
Wait, the robot is writing its own code?
Yes. This program acts as the monitor, constantly checking if the robot is following the rules and on track to achieve its goal.
Hold on. So the robot is making its own code to monitor itself. That's next level. It's like having a self-driving car that not only knows the rules of the road, but also has, like, a super attentive co-pilot who's always scanning for hazards
Aha, that's a great analogy.
and whispering advice.
Right. And the best part is this co-pilot isn't just reacting to things going wrong, it's actively looking ahead, trying to spot anything that could cause problems down the road. And it helps the robot course correct.
So it's proactive. Amazing. And this proactive approach seems to really work. The paper mentioned some really impressive results, especially in a simulated block stacking task. Why is that task so important in robotics research? Seems pretty basic.
Block stacking, yeah, it might seem simple, but it's actually a really important challenge in robotics. It involves precise movements, coordination, and the ability to adapt to even slight variations in the blocks, their shape, their position. It's a great test of a robot's dexterity and problem-solving skills.
So how did CAM do in the block stacking test?
Really well. It significantly improved the robot's success rate compared to other methods. Even a small improvement in those success rates, that can be a big deal in robotics research. It means the system can learn and handle complex tasks, which is exactly what we're looking for.
That's impressive. So what makes it so good at this and other tasks? It sounds like it's all about, like, speed and efficiency.
You're right. One of the biggest advantages is that it simplifies things. Instead of having to process tons of visual data, the robot can just focus on those key constraint elements. The points, lines, surfaces.
It cuts through the noise.
Exactly. And that makes the system super fast. It can react quickly and prevent those errors before they even happen.
So it's not just working hard, it's working smart.
Haha, precisely. And another benefit is that it's surprisingly adaptable. They tested CAM on a whole range of robotic tasks, not just block stacking, and it performed really well across the board.
Oh, wow.
It shows that it's not just a one-trick pony. It can take what it learns and apply it to different situations.
That's a big advantage, especially when we think about robots working out in the real world, where they'll encounter all sorts of unexpected obstacles. Actually, speaking of real world, the paper mentions they even tested CAM with a robot that uses a dexterous hand. A huge step up from stacking blocks. They used a robot hand called the leap hand, right?
Yes, the leap hand. It's designed to be like a human hand, just robotic, so it has that complexity and flexibility. Makes it great for tasks that need really precise movements and control.
So how did CAM perform with this advanced robotic hand? I'm on the edge of my seat here.
It did exceptionally well. The researchers designed some really tricky tasks. Like, imagine a robot that needs to clear a table of objects but leave behind specific ones, maybe anything that's classified as an animal.
So it has to figure out the rule, the category, like a logic puzzle.
Exactly. And these objects could be moved around, even taken away while the robot's working, making it even harder.
Wow, that's tough.
It was. But the results were impressive. It really showed the system could adapt and get the job done, even when things didn't go as planned.
So it's not just following a pre-programmed set of moves, it has to adjust on the fly.
Exactly. The robot showed a real sense of situational awareness, like it understood the goal and could adjust its actions to achieve it, even when things got moved around.
That's incredible. It really sounds like CAM passed its real-world test.
It did, and that's what's so exciting. It shows this technology has the potential to move beyond just the lab into actual real-world applications. It's not just theory anymore, it's a solution to real problems in robotics.
That's amazing. But I'm also curious about the limits. Is there anything CAM still needs to improve? There's got to be some, right?
Of course, like any system, one limitation is that it really relies on visual input. So if the cameras are blocked or the lighting's bad, that could affect how well it performs.
So it's not totally invincible to real-world hiccups.
Right, not yet at least. And that's one area where more research is focused. Also, incorporating more types of sensory input like touch or sound could make it even better.
So giving the robot a wider range of senses to help it understand even more about its surroundings.
Exactly. Imagine a robot that can see, feel textures, hear things, maybe even smell different substances.
That's wild.
Yeah.
It's like giving the robot a complete picture of its world. I can only imagine how much that would improve its ability to learn and adapt.
It's a really exciting area of research, and it shows how this CAM system is constantly pushing the boundaries, evolving.
Well, we've covered a lot of ground in this first part of our deep dive. From the basics of code as monitor, all the way to its amazing performance in both simulated and real-world tasks.
Yeah, we've seen a lot.
But we're just scratching the surface, right? I'm ready to dig into the bigger picture. What could this tech mean for the future of robotics? What are the implications? That's what I really want to unpack.
Absolutely. We're just getting started. In the next part of our deep dive, we'll explore some of those potential applications in more detail. And we'll also talk about why this research is so significant for the future of AI and robotics, the big picture stuff.
Sounds great. Can't wait to uncover more about this groundbreaking technology.
I'm excited to dive in deeper.
Welcome back, everyone. I don't know about you, but I'm still thinking about code as monitor from that first part. It really is incredible to think robots are getting closer to being as adaptable as we humans are. But where does this technology actually fit in, out there in the real world? What are some of those potential applications you mentioned that get you excited?
Oh, the possibilities. They're pretty much endless. I mean, just think about robots working in places that are constantly changing, right?
Yeah.
Bustling warehouses or construction sites, even disaster areas.
Yeah, unpredictable environments.
Exactly. With something like CAMOM, those robots could adapt to like obstacles popping up, maybe even prevent accidents, and definitely get those tasks done more efficiently, reliably.
It's like having a team of robots that can not only think for themselves, but also learn from their experiences, actually get better over time.
Exactly. And they wouldn't just be reacting to what's right there in front of them. They could anticipate what might happen and plan ahead. That would be a game changer.
Absolutely. So what industries do you think would benefit the most from this? What are some concrete examples?
Well, one that jumps right out is self-driving cars. CAM could be huge for making those autonomous vehicles even safer.
Even safer.
Yeah. Imagine cars that can see a collision coming and avoid it way more accurately than we can even do now. Our roads would be so much safer.
I have to admit, that would make me feel a lot better about the whole self-driving car thing.
Yeah,
I know a lot of people, myself included, are still kind of hesitant to, give up control of the wheel.
I get that. Yeah,
But if the car could actually think ahead and see problems before they happen, it definitely makes the whole idea a lot more appealing.
definitely. And it's not just about transportation. Think about healthcare. Robots equipped with CAM, they could help surgeons with really complicated procedures, give them real-time feedback, maybe even prevent mistakes that could, well, have serious consequences.
Wow, that's incredible. The impact that could have on patient care, safety. I always think about robots doing physical tasks, but this is taking it to a whole new level.
For sure. And it's not even necessarily about replacing humans in those fields. It's about enhancing our abilities, pushing the boundaries of what's possible in medicine. That's what's exciting.
What about space exploration? That seems like an area where this kind of adaptability, it would just be invaluable.
You're spot on. Imagine sending robots with CAM to Mars, for instance. They'd have to be super adaptable, able to solve problems on their own, especially with those crazy communication delays between Earth and Mars.
It's like sending a little piece of human ingenuity way out there. And it makes you wonder, what else could we do if we had robots that smart, that autonomous? What challenges could we tackle?
It is exciting to think about. It really feels limitless.
It does. We've talked a lot about how CAM works, how it's been tested, the technical stuff. But I'm curious about the why behind it all. What were the researchers really going for here? What was driving them?
That's a great question. At the heart of it, this research is all about bridging that gap, between just reacting to failures
Mm.
and proactively preventing them.
Ah, that duality.
Right. Most robotic systems, they tend to focus on one or the other, but not both at the same time. CAM was built to do both, which is way more challenging to achieve.
And why is that so important? Why have both?
Because, let's face it, the real world, it's full of surprises. No matter how well we program a robot, how much we plan, there will always be things that pop up unexpectedly, things that could throw it off course.
Like our lobster friend making a run for it.
Exactly. Reactive failure detection, that helps it recover from those surprises, get back on track. But proactive failure detection, that takes things a step further. It lets the robot anticipate those problems and actually avoid them altogether.
So it's quick thinking in the moment and smart planning for the future.
Yes. That combo is what makes CAM so different, so promising. It's not just about reacting to problems, it's about learning and stopping those problems from happening again.
It really feels like a whole different approach compared to traditional robotics. Anything else that sets CAM apart?
Definitely. A big one is the focus on what we call constraint-aware visual programming. What that means is the system isn't just blindly reacting to what it sees.
Okay, so it's not just seeing, it's understanding.
Exactly. It's using those constraints, those rules we talked about, to make sense of what it's seeing. That's how it makes those smart decisions.
So it's seeing the bigger picture, understanding the context of what it's looking at. and then applying that understanding to its actions.
Yes, that deeper level of understanding, that's what's crucial. It's the key to making robots more independent, more capable of handling those messy, real-world environments.
It makes sense. Now, the paper mentions CAM being tested in both simulated and real-world settings, but so far we've mostly talked about the simulations. I'm curious about how it did in those real-world tests. Did it live up to the hype?
Oh, absolutely. In their real-world experiments, the researchers used a UR5 robot arm, which is pretty common in industrial robotics, and they gave it the leap hand, remember, to really test CAM in a realistic setting.
That's a pretty sophisticated setup.
Oh, yeah. And the tasks they gave it were definitely challenging. They had to make sure those tasks needed a lot of precision and adaptability. One example, the robot had to clear a table but leave certain items behind based on a specific rule, like only leave items classified as animals.
That sounds familiar. Like those logic puzzles, figuring out the pattern, the rule, but in this case, the robot's doing it.
Uh-huh, exactly. And remember, those objects could be moved around, even taken away from the robot while it was working, made it even harder.
So not just following a preset program, real adaptability was needed.
Absolutely. And it performed really well, showed that it could handle those changing conditions and still complete the task, even when things didn't go perfectly to plan.
So flying colors in those real-world trials.
Flying colors, which is huge because it shows that this technology has the potential to leave the lab and actually make a difference in the real world. It's not just a concept anymore, it's a real solution to some of those robotics challenges.
That's exciting. But I'm also wondering about limitations. Any areas where the system could still use some improvement?
Oh, definitely. Like any system, CAM has its limitations. One is that it's really reliant on visual input. So if the cameras get blocked or the lighting's bad, that can mess things up.
So not completely immune to real-world problems yet.
Right, and that's one area where researchers are focusing their efforts. Another area is incorporating more sensory input, like touch or sound, that could make it even more robust, more adaptable.
Widening its sensory horizons, giving it a richer sense of its surroundings.
Exactly. Imagine a robot that can see its environment, but also feel the texture of objects, hear sounds, maybe even smell things. That's the future.
Whoa. Giving the robot a more complete picture of the world around it. I bet that would improve its ability to learn and adapt like crazy.
It's definitely a hot area of research, and it's just one example of how CAM is pushing those boundaries, always evolving.
It really is incredible to see how far it's come already. So where do we go from here? Is this just the beginning for CAM?
It definitely feels like just the beginning. This research is a big step, but there's still so much more to discover, to develop in the world of these constraint-aware robotic systems. I'm particularly interested in seeing how CAM could be used with those collaborative robots, the cobots, the ones designed to work alongside humans.
It really sounds like we're entering this new era in robotics, where robots aren't just tools, they're partners. Partners that can learn, adapt, and help us tackle some of the biggest challenges we're facing.
Exactly. And it's not just about making robots more efficient. Think about exploring new frontiers, safer workplaces, even improving people's lives around the world. The possibilities are huge.
That is inspiring. And it makes me even more excited to see what the future holds for this technology and for the whole field of robotics. But before we get too carried away, I think it's important to pause and consider some of the implications, the potential downsides.
That's a great point. Like with any powerful technology, it's crucial to use it wisely, responsibly. In the last part of our deep dive, we'll explore some of those bigger implications of code as monitor, the impact it could have on things like society, jobs, even the future of how humans and robots interact.
Welcome back. We've been exploring code as monitor and all its potential. It's been quite a journey.
It really has.
We've seen how it works, how it can handle all sorts of challenges, even how it could change different industries. But like you said, it's not just about the cool stuff. We got to think about the bigger picture, the impact this kind of tech could have. Putting that much power in the hands of robots, well, literally.
Exactly. It's important to consider the ripple effects, Any big technological leap forward, we have to look at how it might change things for society as a whole.
Totally. So what are some of the big questions that come to mind when you think about code as monitor out in the world? What worries you?
Well, one that always comes up with AI and automation is jobs, right?
Yeah, that's a big one.
If robots can do things that used to need human smarts, dexterity, well, what happens to those people? What happens to their jobs?
That's a real concern, and it's something we've seen throughout history, Whenever there's a big tech change, the workforce feels it.
Definitely. But I don't think it has to be a total disaster. I think it's more about adapting.
Uh-huh.
evolving. We need to start thinking about how we can, retrain people, teach them new skills, skills for those future jobs, jobs that might involve working with robots instead of being replaced by them.
So not robots versus humans, more like
Yeah,
robots and humans teaming up.
exactly. There are things robots just can't replicate. Human creativity, critical thinking, complex problem solving, those will always be needed. It's about using the strengths of both humans and robots to create a workforce that's even better.
Makes sense. It's about remembering that technology. It's a tool. And it's up to us to figure out how to use it the right way, ethically.
Couldn't have said it better. Which brings us to another important thing, ethics in AI and robotics. We're making these systems more and more independent, right? So we need to be really careful, develop them responsibly, and think about the risks.
For sure. So what specific ethical concerns do you see with these super advanced robots? What keeps you up at night?
Well, for one, we have to make sure these systems are used for good, right? Not for harmful purposes. We need safeguards. And we also need to watch out for biases. The data we use to train these systems, it might contain biases that we don't even realize.
That's a good point. It really does feel like we're in this whole new territory. We need like a whole new set of rules, ethical guidelines to make sure we're doing things the right way.
Absolutely. AI and robotics are moving so fast, and it's crucial that we talk about these things openly and honestly. The good and the bad, the potential and the risks.
Well, this conversation has been really eye-opening. It really highlights how this code as monitor, it's got this incredible upside, but we can't ignore the potential downsides either.
I think you put it perfectly. Powerful tool. And like any powerful tool, it can be used in lots of ways. It's our responsibility, us, the developers, the researchers, the people making the rules. We have to guide it, make sure it's used for the benefit of everyone.
Well said. This deep dive into code as monitor has been a real trip. Thank you so much for walking us through all of it, for sharing your expertise.
The pleasure was all mine. Always happy to geek out about AI and robots. Hopefully we've sparked something in our listeners.
To everyone listening, we hope you found this deep dive as interesting as we did. Code as monitor, it's definitely a game changer for robotics. But it also makes us ask some big questions about the future of work, about AI ethics, about how we navigate this tech world that's changing so quickly. So keep exploring, keep asking those questions, keep thinking critically. Until next time, keep diving deep.